Hello, everyone. I just wanted to make a recording of today's material for anybody who needs to be able to go back and not just read a stagnant piece of paper, but actually get some verbal cues as they're reading. So we're going to start off. We're in 12.1. We're looking at vectors in the geometry of space. And of course, we're starting with the geometry of space here. In 12.2, we'll start looking at vectors themselves. To begin with, we have to first understand the three-dimensional coordinate system. So the three-dimensional coordinate system ends up giving us 8 different regions. I said in class how I really like to think of it as like a house where you have 4 rooms in the second floor and 4 rooms in the bottom floor. And you can think of like the literal floor between the first and second floors as being your XY plane. And then you can think of, and I'm pointing to this example or this picture on the right where we have signs. The front right upstairs room is where we are going to have positive X, positive Y, and positive Z. And then we're going to take a tour around counterclockwise upstairs. And so if we go to the back right side room in the upstairs, that's where X is now going to be negative, but Y and Z are still positive. Then we keep going. I should say, and this is also, we have names for these. The first front right room was octant 1, and the back right room in the upstairs, that's going to be octant 2. And then we keep going. We end up in the back left room. That's going to be octant 3. And notice now there's another negative sign. So now X and Y are negative, and Z is still positive because we're still upstairs. And then we finish the tour around in the front left room, where now it is just Y that is negative, X and Z are positive, and this is octant 4. Octant 5, we're going to go downstairs to the bottom right room, and that's right here, where X and Y are positive, but now Z is negative because we are downstairs. And this is going to be octant 5. And then again, we take another tour around in the counterclockwise direction. So if we go back to the bottom right back room, that's where X and Z will be negative and Y is positive. This is octant 6. Octant 7 is invisible to us right now. But in octant 7, it's like diagonally back from octant 5, everything is negative. So octant 7 is hiding in the bottom back left room. All signs are negative. And then finally, we finish up our tour around and we end up in octant 8, where X is positive, but Y and Z are negative. So go ahead and label that. Okay, those are our octants. We got to be really comfortable with that because I'll be referring to different octants and you got to know where we are in the house. In the picture on the left, we talk about planes. We talk about coordinate axes planes, and these coincide with where we have 2 axes. So for example, we've got this YZ plane. That is a vertical plane that is cutting through and right along the y-axis and the z-axis. On the YZ plane, X is equal to 0. Okay. This green checkerboard one, that's the XZ plane, and that's a little hard to read, so I'll just write that, XZ plane. The XZ plane is running parallel to the x-axis and the z-axis, and on the XZ plane, Y is equal to 0. And last but not least is the XY plane. That is like the floor in between the lower octants and the upper octants. And the XY plane is where Z is equal to 0. Okay, so when you read in the homework or in the book, or you hear me refer to one of these planes, what you have to think of is the variable that I didn't mention it's 0. So YZ plane, X is 0. XY plane, Z is 0. XZ plane, Y is 0. Okay? All right, moving on. We have ordered triplets. They're called ordered because we always give them in the same order. It's always X, Y, Z. If we're in 3D and I only give a pair of numbers, so a couple, I don't know where to put it. I need an X coordinate, a Y coordinate, and a Z coordinate always in order to represent any point in space. Now, the way that we get to some XYZ point, I've got this nice picture from online that kind of shows you. But what you'll do is you follow the X directions in the point, right? So however many units X says, and you go up the X axis in counting out those units. And then you'll run parallel to the Y axis, counting out the Y units, whatever they happen to be. And then you'll go up or down, depending on the sign of Z, in order to get your Z value. So, just sketching this roughly, I have a couple of ways that I sketch my X, Y, Z axes. One of them is just like this. I have my X axis, Y axis, and my Z axis. And if I wanted to get to some particular point, X, Y, Z, I'm going to go out by X units on the X axis. Then I'm going to go over, running parallel to the Y axis, however many Y units. And then I'm going to go up to my point P, whatever it happens to be, some X, Y, Z. Okay. And I go up by whatever number of units Z tells me to go up. Now remember, I'm just kind of sticking with the first octant where everything's positive. We have to be able to do this in any octant where anything could be negative. And so we've got this next exercise where we can do that. So in this exercise, we're asked to draw a few octants and then plot the given points. These are the points right here: 2, 1, 3, 2, negative 1, 3, 2, 1, negative 3, negative 2, 1, negative 3. So I'll start off with 2, 1, 3. I'm going to draw myself an XYZ octant. This paper that I'm using is called isometric graph paper. Super cool. Really does help a lot with graphing three-dimensional objects or points. All right, I need to mark off my tick marks on my axes so I can get proper placement. I'll use a different color in order to plot 2, 1, 3. So the point 2, 1, 3, the 2 tells me to go out by 2 units on the x-axis, okay? The 1 says go over by 1 unit in the y direction, running parallel to y. And the z coordinate is 3, which tells me to go up by 3 units. And there's my point, 2, 1, 3. This point landed in octant 1. Okay, the next point is 2, negative 1, 3. So again, I will draw my XYZ octant. And I will put in my tick marks. And then I'll get to work. So again, we're going to go out 2 units by X. That didn't change. Now, instead of going to the right by 1, I have a negative 1 here for Y. So I'm going to put in dashed lines over here to indicate the negative side of my Y axis. All right, so negative 1 tells me I should go left by 1 unit, running parallel to the Y axis. And then finally, the 3 in the Z coordinate tells me to go up by 3 units and then plot my point. This point is in the 4th octant. Okay, 2 more, and then we'll be done. 2, 1, negative 3. All right, I'm going to draw my octant. And get in my tick marks. And I notice I have a negative Z value. So I'm going to go ahead and draw in my negative z part of the axis with dashed lines. Okay, I think I'm ready to go. All right, we'll go out by 2 again for the x value. We'll go over by 1 again for the y value. But now for the z value, we will go down by 3. That's 1, 2, 3. Here's my point. It looks like this is in the 5th octant. It is downstairs. All right, final point is -2, 1, -3. All right, so I can see right away I need a negative x and I need a negative z axis as well. So I'll start off with my regular old xy z octant, but I'm going to add in the dashed lines for the negative x as well as for the negative z. Okay. We will go, instead of going out by 2, we're now going to go in by 2 because it's a -2 for x. Oh, I should put my tick marks in there. Get everything in. Okay, so I'm going to go in, so along the negative part of the x-axis all the way to 2. There we go. Then I'm going to go right by 1, running parallel to the y-axis. And then I'm going to go down by 3 over here. It looks like we are in the 6th octant. Okay, now we don't graph points too often, but they can be helpful, especially with a couple of the problems that are coming up. But it's just good practice to see how it's done. I do recommend this isometric graph paper. It is in the notes that are posted online. So, you can download what I've got there, or you can just do a Google search on isometric graph paper. All right, continuing on. The distance formula sounds like something that you learned a long time ago, and it is. But what we have to do is we have to take what we know from 2D and extend it to 3D. So the good thing is that the old-fashioned distance formula that I have right here, d is equal to the square root of the sum of squares of the difference in the x values and the difference in the y values, would equal the distance between 2 points. For 3 coordinates, so x, y, and z, now when we find the distance between 2 points, we don't have much of a reach to figure it out. We just need to take into account that there's also z components. And so we need to look at the difference in the z values and square those and go ahead and add that into our sum of squares. We got a nice visualization to kind of give you an understanding of that distance from like the origin out to some point in space. But let's go ahead and use it. We've got an example right now. The distance between the 2 points, P, which is 2, -1, and Q, which is 1, -3, 5. So we're going to just plop that right into our formula. D is equal to the difference in the x values. So I'll start with the first one and subtract the second one, 2 - 1 squared, plus the difference in the y values, -1 minus a -3 squared, plus 7 - 5 all squared. Simplifying, this becomes 1 squared. -1 minus a -3 ends up being a +2 squared. And then 7 - 5 is 2, so we get another 2 squared. This is going to add up to a nice square root of 9, which is 3. Okay, so that's pretty straightforward. Not much of a reach from what we did many, many years ago in algebra. Now, of course, things don't always stay so nice, so we have to think about distances now. We're in 3D, so it's not always just, explicitly given points that we have. Sometimes we have to go searching for the other point, but we have enough to find it. So in this particular example, we're told to find the distance between a point P, which is 4, -2, 6, and the y-axis. So I'm going to draw this because it helps to see it. That's really the only reason. There's a negative y value, so I'm going to get in my negative y value. Okay. I don't need to be exact in my drawing. I just have it just needs to be clear enough for me to see what I'm doing. So this point is telling me to go out by 4 on the x-axis. So I end up here. It says to go left by 2, running parallel to the y-axis. So I end up right here. And then to go up by 6. 1, 2, 3, 4, 5, 6. All right. Here's the point P. Okay. Now, if we're trying to find the distance between the point P and the y-axis, the closest point on the y-axis to our point is the point where y is equal to -2. It's over here, right on the axis. So we're trying to find this distance right here. Okay. We have our point P, but this point on the y-axis, let's see. So if it's on the y-axis, then the x value is 0 and the z value is 0. So 0, comma, and then 0. The y value is at -2, and I chose -2 because the y value in the original point was -2. So I'm trying to get the shortest distance between 2 points. So I'm going to have a -2 for my y value in my point. Well, then from there, I can just go ahead and use my distance formula, where one of my points is P and the other point is the one I just stated, 0, -2, 0. So what this gives me, I've got my difference in x values, 4 minus 0 squared, plus -2 minus the -2, all squared, plus 6 minus 0, all squared. This simplifies to be the square root of 4 squared plus 6 squared, which is the square root of 52. And that's good. Now, what some people noticed in class was that we could look at this in a different way completely. Like, for example, if I was to kind of give myself an extra dashed line in there, I'd see that I actually have a triangle. And I know the lengths of the legs. So the triangle has a height of 6, it has a base of 4, and I don't know what its hypotenuse is. But I do know the Pythagorean theorem, right? C squared is equal to A squared plus B squared, which in this case is going to be 6 squared plus 4 squared, which is 52. And that means that C, we'll call this C, is equal to the square root of 52. So either way we look at it, we get the same answer. It's just you have to decide how you best see things, okay? All right, next one, we're supposed to find the distance between the point 4, -2, 6, and then the xy plane. So if we go back to our picture up above, that point P is just in space. It's just like a dot hanging out in the middle of space. And I want to know, like, how far is it basically from the floor? You could even think of it as like a little tiny ball that you're holding up in the middle of space and you drop it. How far is it going to travel until it hits the floor? Well, we already know from before that the height right here is equal to the z value, which was equal to 6. So that totally works. I could just think of it that way. Or I can also realize what this point actually is. This point has the same x and y value as the point P. So 4 and -2. What's different is the z value because now it's on the floor. So the z value is 0. So I could use the distance formula, and the distance will be the distance between the point P and then this new point that I found on the xy plane. Okay, so then I get 4 minus 4 squared plus -2 minus a -2 squared plus 6 minus 0 squared. Well, that just simplifies to the square root of 6 squared, which is 6. And that's the same as the height of the original triangle, or the original drop, okay? All right, moving on from distance, we get to circles and spheres. One of the things I pointed out in class was that if you were to take the distance formula, let's just show it right here. The distance is square root of the sum of squares of x2 minus x1 all squared plus y2 minus y1 all squared. If we square both sides of this, then what we get is d squared is equal to x squared minus x2 minus x1 squared plus y2 minus y1 squared. And that is identical up to, a few names. It's identical to the formula for a circle. So the definition of a circle, it comes from distance. The equation of a circle gives you the set of all x, y values that are equidistant from some center. That's it. That's all it is. So in this particular formula that I've typed in here, we have a circle that's off-center, and it's off-center by some h value, which is an x value, and some k value, which is a y value. And then the r squared is the radius squared. Okay, so we should be able to find our centers and our radii from the equation of a circle. Now, if h and k are 0, then the circle is centered about the origin. And so that would be like this sloppy little circle here having a center of 0, 0. And its equation would be x squared plus y squared is equal to r squared. Okay. Let's see. Next thing. Let me take that out of there. Okay. We want to be able to extend a circle over to a sphere because we are going to be working with 3D. The great thing is that you could almost picture, like you ever take a coin, like a quarter or something, and spin it? And if it moves fast enough, you can almost see a spherical shape coming out of it. That's the same idea here. We can imagine a circle that's just being spun, and what comes out of that is a sphere. It's a ball shape, right? It can be off-center. It does not have to be centered at the origin. And if it is not centered at the origin, then here's our standard form. X minus h all squared plus y minus k all squared. That's still the same as a circle. The added component is z minus l all squared. And that's what gives us our sphere. Still equal to r squared. We're still dealing with a radius. Nothing changed there. But once you've got an equation in this form, you can identify that HKL is the center, and then R is the length of the radius. Okay. And this picture here is just the special case where the sphere is centered on the origin, which is primarily what we'll be dealing with when we get to the point where we're working with spheres more. So I have some problems we can work through here where we're just dealing with spheres. Start with like the simplest type of problem that you might see in the homework that might not actually be simple because it's going to require us to remember how to complete the square, which it's been a while. So most people aren't going to remember, and that's okay. Let's go ahead and walk through this. All right, so we're asked, what is the center and radius of the given sphere? Now, it's easy to look at this question, just throw up your arms and say, I don't know. I have no idea. It's not written like that form you gave me. And that's true. But we can rewrite it. So the first thing I'm going to do is notice that everything on the left-hand side is divisible by 4. So I'm going to divide everything, left and right, by a 4. What that gives me is x squared plus y squared plus z squared minus 2x plus 4y is equal to 1/4. Okay. Now what I need to do is I need to group my x things together and my y things together because they both have 2 items that have their variables in them. So when I regroup, I have x squared minus 2x plus y squared plus 4y plus z squared is equal to 1/4. Okay, now going back up and looking at the standard form for a sphere right up here, It looks like I need like my x squared minus 2x. That's not going to do. That needs to be factored, but it only has two terms, and I'm not going to write it as x times x minus 2. That doesn't give me any information. What I need to do is complete the square on that. So I'm trying to figure out what number can I add to x squared minus 2x that will make it a perfect square trinomial that I can factor. And then the y squared plus 4y, same thing. I need to complete the square on that. I got to figure out what can I add to make that a perfect square trinomial. So I'm going to write this one more time before I figure those things out. I have x squared minus 2x plus something. I don't know what the something is. Okay, I'll figure it out. Plus y squared plus 4y plus something. Again, I'll figure it out. Plus z squared. Now z squared is good. Z squared is like my favorite thing in this whole equation because z squared is standing alone. There is no plus something at z. It's just z squared. So if we compare that to the standard form that's up here when the center is at 0, 0, 0, it looks like z squared is, if we have a z squared showing that, then my z component for the center must be 0. So I don't have to play with that at all. And then from there, equals 1/4. Now, golden rule, if you're like doing stuff to equations, is if you're going to add or subtract something on one side of the equation, you better be doing it on the other side. So on the left-hand side, I'm adding two things. That means on the right side, I should be adding two things as well. Okay, now let's figure out what those things are. Way, way, way back when we were first learning completing the square, we were given something like ax squared plus bx plus c is equal to 0, something like that. And we were told, actually, I'm going to write this as, start over. If we were given something like x squared plus bx plus c equals 0, and we were told to complete the square on this, we were told to take the b value, whatever's in front of the x, we take b over 2 all squared, and we're going to add this into the equation. And it's going to make me have a perfect square trinomial. So let's see, okay? Underneath the x squared minus 2x plus the blank, if I'm looking at b over 2 all squared, b is negative 2 here. So negative 2 over 2 all squared, that's going to give me a negative 1 squared, which is 1. So that means I'm going to add in 1 on the left, and I'm going to add in 1 on the right. Then for the y squared plus 4y, I have to do the same thing. I'm looking at b over 2 all squared, b is 4. So I'm looking at 4 over 2 all squared. 4 over 2 is 2. Square it, we get 4. So I'm going to add in a 4 on the left, and I will add in a 4 on the right. Okay, now on the left I have x squared minus 2x plus 1. And I like to use the factors of AC that add up to B in order to figure out how this factors. So I look at factors of A times C that add to B. So in x squared minus 2x plus 1, A equals 1, B equals negative 2, C is equal to 1. Okay, so AC is equal to 1. We want to think of two factors of negative 1 that will add up to negative 2. Well, first things first is that they both have to be negative if they're going to multiply to give me a positive and add to give me a negative. And the only ones I can think of that would multiply and give me a 1 are negative 1 and negative 1. If I add those together, it equals negative 2, which is my B. Okay, so that's how I'm going to work the factoring on that one. I know that it's going to factor as x minus 1 times x minus 1, since minus 1 and minus 1 were the factors of AC that add up to B. I do the same thing for the y squared plus 4y plus 4. Here, so break this into chunks here. maybe not quite that long. Okay, here I have A is 1, B is 4, C is 4. So A times C is 4. The factors of positive 4 that add up to 4, they should both be positive so that they multiply to be positive and add to be positive. And they should be 2 and 2. If I add these, that's equal to 4, which is B. Perfect. That means I'm going to factor this to be y plus 2 times y plus 2. The z squared just gets to like come on down and be part of the game. So we have plus z squared. And then all of this is equal to, I have 1/4 plus 5. Now, one word of advice I want to give you. I know that mixed numbers do exist, but we don't use them. It's better to write an improper fraction than to use a mixed number, just because it is easy to misinterpret what a mixed number is. It can look like a whole number times a fraction instead of it being a whole number plus a fraction. So try to avoid the mixed numbers. It might save you some grief on WetAssign. Okay, I'm going to rewrite this and then we're almost done. So this becomes x minus 1 all squared, since there are 2 of them, plus y plus 2 all squared, since there are 2 of them, plus z squared, plus, if I rewrite the 5 as 20 over 4, sorry, that shouldn't be plus, that should be equals. If 5 is 20 over 4, then my total sum is 21 over 4. And that is the equation of the sphere. The center, I pull out from finding the x, y, z values that would make everything on the left be 0. So if x was 1, that term would be 0. If y was negative 2, that term would be 0. And if z is 0, that term would be 0. My radius is always the square root of the number that is on the right-hand side. So the square root of 21 over 4 or root 21 over 2. Okay. I think, did I answer the question? So that's what you always want to do at the end of a problem. Like, did I actually answer the question or do I still have more to do? We answered it. They wanted to know what's the center and radius. I gave it to them. Next problem. Find an equation of the sphere which passes through the point 0, 1, negative 1, and is centered at 3, negative 1, 0. What they've given us, I'm going to attempt here to draw a sphere. They've given us a point that is the center. So that's the 3, negative 1, 0. They have given us another point that is a point on the edge of the sphere. I'm going to go ahead and put it like right over here. I guess it should be going down. Sorry. Maybe that's not what I wanted to do. Hold on. I have to redo a sphere once I mess the sphere up. Hold on. Okay, center's right here. And then we have a point maybe right here. Okay, so this is the point 0, 1, negative 1. And then I have my center 3, negative 1, 0. So they gave me a center. At the very least, I know that the equation of my sphere is x minus 3 squared plus y minus a negative 1 all squared plus z squared is equal to, they didn't give me a radius. So at the best, I can say r squared, and that's it. I don't know what it is. So when we're working with these problems, it's good to write down what it is that we know. So drawing a picture of what you know, writing down any equations of what you know, those are important factors that you've got to get down. Then, you ask yourself, what is it that I still need? So we still need r squared. And the way we're going to get r squared is we're going to take advantage of the fact that we have a point at the center and we have a point on the edge of the sphere. That is going to give us our radius. Okay, so if we could just find the distance between those 2 points, we're good. Here's another way, and I saw a lot of people in class kind of intuitively using this way, so I'm going to use it too. They were just taking the point on the edge and plugging it into the equation of the sphere, and that gives you r squared. So let's try that. We're going to plug 0, 1, -1 into the sphere equation to find r, or really r squared. So when I plug it in, I get r squared is equal to, the x value is 0, 0 minus 3 all squared, plus, I have y plus 1, so it's going to be 1 plus 1 all squared, plus z is -1 all squared. Okay, continuing on, this gives me -3 squared is 9, 1 plus 1 squared is 4, 1 squared is 1. This is giving me 14. Okay, that is the missing piece. That's my r squared. So the equation, that's what they're asking us for, is x minus 3 all squared plus y plus 1 all squared plus z squared is equal to 14. And we're done. Okay, here's the next one. Find the equation of the sphere with a center at -3, 2, 5 and radius 4. I'm not even going to read the second part of this question yet. I'm just going to write down what I've been given. They're telling me the center, they're telling me the radius. I can go ahead and come up with the equation of this. So using my form, this is going to be x minus a -3 all squared plus y minus 2 all squared plus z minus 5 all squared is equal to 4 squared. Okay? Now, what is the intersection of this sphere with the YZ plane? The analogy I gave in class was that one of the walls in the room was the YZ plane. And what we have to imagine, and I'll draw it here, kind of what we were looking at in class. The YZ plane coincides with the YZ axes. X has nothing to do with the YZ plane other than X takes on one value and one value only. If you're on a plane, an axis plane, that means that the missing variable must be 0. So the analogy that I gave people was, imagine I have a bowling ball and I throw it at the wall, right? A bowling ball is a sphere. And I'm imagining that my bowling ball has a radius of 4 units, okay? Now, when I throw it at the wall, it gets lodged in the wall and it's just kind of stuck there. And that's this equation right here, okay? But it's this equation for a fixed x value. So the bowling ball gets stuck in or lodged in the wall. On the YZ plane, where x is equal to 0. Okay, so we're on the YZ plane that fixes x to be 0. And the biggest question, and I think probably the biggest confusion is, well, what do I do with x equals 0? Where am I supposed to put it, right? When we're trying to find an intersection of two different shapes, in our case, one of the shapes is the plane, one of the shapes is a sphere. What we do is we take the equation of one of them and we substitute it into the equation of the other. X equals 0 is the equation for the YZ plane. So we substitute. The equation x equals 0 into the sphere, to find the circle of intersection. It didn't seem like people struggled too much with identifying that if you throw a bowling ball at a wall and it gets lodged in the wall, the intersection of the ball with the plane or the wall will be a circle. The question was, how do we come up with that circle? We're going to substitute x equals 0 in. So here's what happens. I plug in 0 plus 3 all squared plus y minus 2 all squared plus z minus 5 all squared is equal to 16. Now the y and z stuff, I'm just going to leave that alone. There's like nothing for me to do there. But that 0 plus 3 squared, that's just 9. Okay? So I have 9 plus y minus 2 all squared plus z minus 5 all squared is 16. Move the 9 over. That's going to give us the equation of the circle that we want. So we have y minus 2 all squared plus z minus 5 all squared is equal to 7. And then, so let's see, what's the question? What is the intersection of this sphere with the YZ plane? So I'm going to have my conclusion statement. The intersection is a circle with radius root 7 and center 2, 5. I should say actually, because it's not just 2, 5. X was in there. 0, 2, 5. Okay. That's a big thinking problem, and you could look at it from other angles too. Like what happens if it was finding the intersection of the sphere with the XY plane, or like, is there an intersection with all the planes, right? And it depends on how far away that center is from the plane, right? With a radius of 4, I don't think this is going to actually hit the XY plane, but it will hit the XZ plane. So, think about the different angles on this. You might be forced to in the homework as well. All right. So in the next example, I gave 5 different equations or inequalities for you to start thinking about, and then come up with like a rough picture and a description in words. So the first one is z is less than 5. And I'm going to go ahead and just try to draw what that means. But first, I'm just going to draw my axes. X, Y, and Z. And I'll stick 5 right about here. Okay. If Z was equal to 5, that would be a horizontal plane. Because X and Y are not mentioned in the equation, that means that X and Y get to take on all values, all real numbers. So this is an infinite plane that cuts through the Z-axis at 5 and runs horizontally, okay? Now, if we want to describe what Z is less than 5 is, then we're not actually going to include Z equals 5. We just want all the space in the world that is below 5. That's what Z less than 5 means. So we would call it a half space region below the horizontal plane Z equals 5. Now to draw this, I don't know if I really can or not. It's a kind of a rough sketch, but let's see. So I could kind of give myself a plane. Let's say that goes through at Z equals 5. And I'm going to make sure that I have dashed lines all through here. The space below this, that's about as good as I can do. Not looking for perfection here, just like a rough idea. The point is, though, that I did not include the plane Z equals 5. I just, filled in the space below it. All right, next one. It looks like I have an equation for a sphere. we're looking at x minus 1 all squared plus y squared plus z minus 1 all squared is less than or equal to 2. Okay, we just got done doing spheres, so we know that this is a sphere, okay? But there's this inequality in there. And like, what does that mean? Think about that a moment. Like, you know, just we could think of a few different objects. I think if you were to imagine like a basketball is filled with air, right? There's nothing in the middle of it. It's just like the skin of the basketball on the outside. And imagine it's, you know, infinitesimally small, the thickness of this basketball skin. But inside, it's just air. A sphere, by definition, is the set of all points that are equidistant from some center, right? It's not the stuff inside. It's the stuff that's right on the edge of the sphere. That's the definition. So if I want to come up with a sketch of what this means, this inequality is saying not only do I want the set of all points that are equidistant from this center to the edge of my sphere, I also want all this stuff inside. So that's more like, I don't know, you can imagine like if somebody made a sphere made out of cement, then the cement fills in the space inside. So we want everything. We want it all, including the outside. So it's the edge and the inside of the sphere. I'm not going to draw an XYZ axis on this because I'm terrible at drawing off-center axes on a sphere. So the more important thing is to be able to describe and just give a rough sketch. We all know what a ball looks like. Here it is. Okay. The next one, though, is very similar to this. In 3, I believe we're looking at, same equation. So x minus 1 all squared plus y squared plus z minus 1 all squared is greater than 2. I'm going to draw my ball again. Okay. Remember, the equation of a sphere gives you the set of all points that are equidistant from some center. So if we're saying that the set of all points is greater than 2, then we're not talking about the sphere. We're talking about outside the sphere, because the sphere is the set of all points that are square root 2 units away from the center. So we want everything outside and not including the edge. So I'm going to very roughly put on these dashed lines. We don't want the outside. I'm sorry, the edge. So it's the outside the sphere, not including the edge of the sphere. Okay. And finally, another one. X squared plus z squared is equal to 1. All right. Well, we've been working with these. The equation of a circle that is centered at 0, 0. This looks like a circle with center 0, 0, except it's x and z. That's kind of weird, right? I'll just say at the origin. That keeps it simple. And radius 1. Now I'm going to try to draw it, okay? That's what's going to be a little weird. I'm going to draw a 2-dimensional axis with the horizontal axis being x and the vertical axis being z, not y, but z. And I'll draw a unit circle on here. Okay. Now, I want to translate this to, what happens when I have a y-axis on here. Okay. So I'm going to draw, so this is in 2D. In 3D, I'm going to we have x, y, and z. I'm going to go ahead and put in that unit circle here. Okay, so that is my circle with center at the origin and radius 1 on the xz plane. But like, what's going on with y? That's the hard part. So this equation is true for all values of y. Because y is not in the equation doesn't mean that it's undefined. It means that it's defined for all y values. I don't care what you throw in. I'm going to give you a circle of radius 1. If y is 3, my circle has a radius of 1. If y is -7, my circle has a radius of 1. And it's always a circle that is running parallel to the xz plane every single time. So I could draw, another circle out here, and I could connect these. And what that's giving me is what we call a circular cylinder. Kind of weird. So if there is a missing variable, in our case, the missing variable is y. If there is a missing variable, draw the equation as you would in 2D, and then drag that shape along the axis of the missing variable. So draw a shape as you would in 2D. Then drag this shape parallel to the axis of the missing variable. So that's what I have right here, right? So we have a circular cylinder that is symmetric about the y-axis. Okay, last one. And I go, whoops. This one is a little bit different. So in 5, we're given our equation in set notation, and really that's because we don't have a way to write this type of equation yet. We will though. So it's the set of all x, y, z ordered triplets such that x is 3 and y is 4. We have to remember that and in math equals intersection. Okay? Or would be union, and is an intersection. So, and we also have to remember that, like in algebra, when we were graphing, if I told you x equals 3 is the equation, you would draw me a vertical line going straight up and down. And if I told you y equals 4, you would give me a horizontal line going through y equals 4. But we're not in algebra anymore. We're in Calc 3. We're dealing with a 3D world. So when we draw these things, they're not lines. They're actually planes. So just like in number 1, this is why I'm doing 5 next to 1, because it's a perfect parallel. We're in number 1, we're looking at z being less than 5 and having to first think of, well, what is z equals 5? And that was a plane that was horizontal to the xy plane. X and y were not involved in the play except that they could take on any values. Okay? So if I give you that x is equal to 3 is an equation, what that is a vertical plane that is going to go through x equals 3. So that's kind of hard to draw, but what I'm going to do is first just draw Oops, not what I meant to do. I'm just going to draw the line that goes through x equals 3 and then kind of a short plane. We have to imagine this does go up infinitely and it goes down infinitely and it goes left and right infinitely, and it is always parallel to the z-axis and the y-axis. Now, the next piece is y equals 4. Okay. Now, for this, I need to draw first a line that goes through y equals 4 and runs parallel to the x-axis. And then I'm going to kind of draw that. Okay, there's this intersection point right here. This point has a value where x is equal to 3, y is equal to 4, and z is equal to 0. Okay? And there is a line of intersection where the two planes are crossing. And that's what this is, okay? So when we're asked to draw a picture, here's our picture, and we want to describe in words. Our description is that this equation is the line of intersection of two vertical planes. That's about it. Oh, that goes through, because this can help place us. 3, 4, 0. That's all I can say for the description. That pretty much gives us a placement in space. We have a point that it goes through. We know it's vertical, so we can just extend upward to get our line. Okay, that is it for the notes from 12.1. We will do a little group work working on different surfaces next time, and then we'll get started on 12.2 with the vectors. We do have a quiz on Wednesday. It's a mini quiz just over some of the basics from 12.1. Be sure to get into WebAssign, get your homework started, if not done, by Tuesday night. Please do note, and I didn't say it in class, but it is in the syllabus, the makeup policy is everybody gets a grace period of 2 days. So if you don't finish it by Tuesday night, it's okay. You can wait until the due date has passed and do an automatic extension. No points taken off whatsoever. You get 2 more days to work on your homework. If you have any questions while you're working on the homework or just anything we did in class or how this course is run, please just reach out to me. I'm available by email and I will answer you as fast as I can. See you Wednesday.